Hi, I'm Dikshita. Today I'm going to talk about the project called Closest Pair of Points, where I used brute force algorithm and the divide and conquer algorithm. So for this project, I focused on analyzing and comparing the performance of the two algorithms to solve this problem. I actually implemented both the brute force method and more efficient divide and conquer algorithm, all using the Python in the Jupyter notebook. Since the Python is interpreted, there's no need for compilation. Everything runs directly by executing the notebook cells. So for this generation, I created random sets of 2D points using Python's random module. The sizes of these inputs are ranged from 10,000 to 55,000 points. And just to ensure the consistency and fairness, both algorithms were tested on the exact same set of points for each value of n. I couldn't run this code right now because it's gonna take too long to execute. So I already run it before, and I'm gonna show right now. So the brute force version is simply to check all the possible pairs of the points, and it computes their distance, which gives us time complexity of like O of n square. So the divide and conquer version is much smarter. It sorts the points and recursively breaks down the problem, resulting in O of n log n performance. To measure this performance, I use the timed into time function to track the smart and end of each run. For every input size, I ran both algorithms 10 times and then averaged the results. This helped reduce the effect of random noises and gave us more accurate timing data. So the results include the theoretical runtime, the average empirical runtime. So here we can see the results for input sizes from 10,000 to 55,000 with the average runtime and the empirical runtime. All of this was organized into a table to help compare and visualize the performance trends. And as expected, the divide and conquer algorithm performed significantly better than the brute force method as the input size increased. Where we can see in the first table, the input size is 5.05, and in the second table, the input size is 7.05. So here we can see that the divide and conquer algorithm input sizes is increased. So overall, in this project demonstrates like how different algorithmic strategies impact runtime efficiency. Ensured that the inputs were consistent, the execution was fair, and the timing was accurate across multiple runs. Here are my graphs for brute force algorithm and for the empirical runtime versus the predictor runtime, and empirical runtime versus the predictor runtime for algorithm 2. This is my first graph for the empirical running time comparison. And this is my second graph for the algorithm 1 empirical runtime versus the predictor runtime based on the input sizes and the values. And this is my second algorithm for empirical runtime versus the predictor runtime for the second algorithm. So, yeah, that's the work I did from designing and implementing the algorithms to generating inputs, timing their performance, and compiling the results. Thanks for listening. Thank you.